This podcast is brought to you by LMU Munich.
Hi, okay, so this is my final lecture. This is going to be on trying to use holographic approaches to look at far from equilibrium dynamics. Some of you who were here last week for the conference may have heard parts of this before, but given that actually I've got lots more time than I did in that lecture, and also there were lots of questions, I'll try and actually add some more background material, both coming from the solid state, but also a few more details on the holographic side. So I should say that, you know, a lot of this work that I'll talk about was done in collaboration with Jerome Gauntlet, Julian Sonner, Toby Wiseman, and Ben Simons. So that's, you know, quite a collection of people. So Jerome works on M theory, Julian's a string theorist, Toby works on numerical GR, he's a cosmologist, Ben's a condensed matter theorist. And I think what I found particularly exciting about this work was just that by combining all of these different perspectives, you start to gain insights into problems that would probably be quite hard otherwise. And so I think there is a lot of potential going forward for this area of non-equilibrium systems. And the question is just how to target those kind of problems that are going to have the closest connection to condensed matter systems, okay? And that's actually not so straightforward. But what I'll try and convince you of is that there's enough interesting problems out there that I think a lot of connections will develop, okay? And the last part of my talk is some ongoing work. It's actually rather premature to be talking about this, but again, I think there's enough clear reasons for why we want to look at this problem that it's worth talking about, okay? And so this is some work done in collaboration with Benjamin Doyon, who's also at King's College London, Conrad Sharm in Leiden, and two of his students as well, okay? So what I'm going to do is I'm going to start off by trying to give some experimental motivation for looking at non-equilibrium systems, okay? So many of you will know that, you know, there's been huge advances looking at the properties of ultra-cold atomic gases. We've seen figures where we look at phase transitions between, say, superfluid and a Mott insulator. But the thing that's very interesting about these cold atoms experiments is they can be very clean and well isolated from their environments. And so you can start to look at the non-equilibrium dynamics of a coherent quantum many-body system in a way that's previously been very hard to do. Okay? Now, in particular, although the actual experiments I will talk about, if you just looked at them as cold atoms experiments, you wouldn't necessarily be able to realize these directly in an ADS-CFT context. Okay? On the other hand, I think if you look at these experiments from slightly broader perspective, you see that actually there's rather close parallels and analogues of questions that you could ask about ADS-CFT models, which might start to actually help understand various properties of ADS-CFT, okay? So we looked at a couple of problems, as I said, related to holographic superfluids with Jerome Gauntlet and Toby, and also this problem of heat flow between CFTs. And these were largely motivated by a huge amount of work done in both the condensed matter literature and also the ADS-CFT literature on looking at what are called quenches. Okay? You imagine you want to try and understand the far from equilibrium dynamics of an interacting quantum system, you've got to decide how you're going to kick this out of equilibrium. Okay? And one possible route is to perform a so-called quench, where you suddenly change a parameter in the Hamiltonian or your holographic system and ask how it evolves with time. Okay? Now, of course, there's many other types of protocols you could do. You could have various sweep types experiments, and all of these things do actually crop up. Okay? And so the basic question is just to try and set up very simple paradigmatic examples of non-equilibrium processes where you can maybe shed light on organizing principles out of equilibrium, okay? I mean, if you just think about the spectacular achievements in classifying equilibrium states of matter, it's a shame in some respects that we don't have such tools for non-equilibrium states, okay? Somehow every non-equilibrium problem looks rather different, and yet surely some of these things must share common features, okay? And again, I think that's some place where ADS-CFT might be able to help in a way that at the present in condensed matter, we're probably struggling to get beyond integrable systems, okay? So I'll give you then kind of current status and future developments. Okay? So let me just talk about some experiments. Okay? So maybe some of you have seen these. I mean, just out of curiosity, who would say that they're very familiar with experiments going on in cold atoms? Okay, so good. Okay, so perfect. So let me tell you then about 3 experiments. Okay, they're all rather different experiments, but they kind of illustrate the kind of power of these cold atomic gases, but also they raise a lot of questions that are rather challenging, okay, and rather broad in character, okay. So this was some pioneering experiments done in the group of David Weiss, where he looks at the non-equilibrium dynamics of a 1D Bose condensate, okay. So what they do is they put these atoms in a trap, okay? So first of all, you have to make these 1D condensates, so they use laser beams to make a lattice, okay? And if they make the confinement in one of the directions particularly strong, you can make arrays of 1D chains, basically, okay? So this is a kind of bunch of 1D systems, and then what you can do is you can make the atoms go in opposite directions in this 1D tube, okay? But because you've got some trap to stop the atoms flying out, they kind of go up this hill and come back, okay? So basically what you're trying to do is you're trying to set up some analog of this Newton's cradle experiment, but using ultra-cold atomic gases, okay? And so you see this is this kind of broad trap that's keeping the atoms. You apply a momentum pulse to give some of the atoms a momentum in this direction, some in that direction, and so they oscillate backwards and forwards, colliding twice every full period of oscillation, okay? And so then what they do is they take these atoms that are being forced to undergo these repeated collisions, and they then release the trap, and then they can image the atoms, okay? And so what you can see here is this is at time t equals 0. They're bringing the atoms together, they collide, and then they go apart, and they can repeat this many, many times, okay? And the basic point of this paper was to demonstrate that even after many thousands of collisions, okay, these Bose-Einstein condensates don't equilibrate, okay? So this has been attributed to the possibility of the role of integrability and conservation laws in these 1D systems, because if you have a large number of conservation laws, they may actually inhibit the equilibration or the thermalization process in these strongly correlated systems. And there's now been a huge amount of activity in the integrable models literature trying to really flesh this out in some detail, okay? So that's one class of experiments, okay? So let me and I should say, if there's any questions, please do interrupt and ask. Okay? So here's another set of experiments that were done in the group of Dan Stamper-Kern, Berkeley. Here, he's taking a spin 1 gas, okay, of rubidium atoms, okay, and they have an effective Hamiltonian which has 2 terms in it. Okay, let me just turn on the light. Okay. So it has a term that's proportional to expectation value squared plus, actually I'll probably put that in the wrong way, okay, with some coefficients alpha and beta, okay? So there's some effective energy describing this system, and the basic point is that alpha turns out to be negative in their experiments, so this one wants you to magnetize and form an ordered state, whereas this term is something they control with a magnetic field. It's proportional to b squared. It's a quadratic Zeeman effect. And this one, on the other hand, wants you to have Sz equals 0, and in particular doesn't want you to magnetize, okay? So what they do is they start from a high field regime where this term doesn't want you to magnetize, and then quench into a phase where you do want to magnetize. Okay? And then the question is, what happens? Okay? So what they're showing here is some data from these atomic clouds. Okay? So it looks like a kind of cigar-shaped cloud. A certain time after they perform this quench. Okay? So they go through the phase transition into this ordered state. And what you see is, as a function of time, you see these little domains forming with different colors. And what they correspond to is the magnetization in the XY plane, okay? So this is both the amplitude and the phase of the magnetization. So what they're seeing is the evolution of domain formation in these condensates, okay? And I should say that actually this isn't one condensate that they're following the domains for as a function of time. They do repeated experiments after different waiting times to see how these structures evolve, okay? Now, again, this is the kind of thing you could imagine asking within the context of ADS-CFT, okay? We'll actually look at some examples of looking at quenches, but just how do domains form, okay, in some interacting quantum system, okay? Now, here, I mean, you know, they can get quite a lot of insight because you can look at the early time dynamics in these systems. They have a kind of instability that makes these domains grow. And what you're trying to get a grip on is, you know, what controls the time scale and the length scales of these domains, okay? But in general, if you take some interacting quantum system and you quench it, you're going to get some inhomogeneities form. And then there's interesting dynamical questions about what controls the time scales for the growth of these domains and, you know, how do they thermally equilibrate, okay? Now, what's more is that they can also see in these experiments topological defects, okay? So here, they're just zooming in on a little part of one of these clouds, and this is a plot of the amplitude and the phase, and what you see is you go around here, and you go from bright to dark, meaning your phase is circulated by 2 pi, okay? So these correspond to little topological defects where you have a non-vanishing spin current, okay, in this system, okay? And of course, the classification of topological defects depends on what system you're looking at. So here they're looking at topological defects in a particular model of a spin-1 condensate. But again, you could imagine all sorts of interesting topological defects in systems with non-abelian symmetries, for example, okay? And again, you know, there's questions about how such defects would proliferate, what would control their timescales for interactions, et cetera, et cetera. And again, these are rather difficult problems to get a grip on, okay? And some of you may also be aware of these very nice papers by Alan Adams and Paul Chesler looking at superfluid turbulence, okay? Again, it's a time-dependent type of experiment. You're putting vortices into a superfluid and asking how does energy transfer between length scales in these systems. Again, very challenging problems, okay, that you might be able to get a handle on using these techniques. Okay. So then let me just tell you about this last experiment, okay? Now, on the face of it, this experiment won't seem to have very much to do with ADS-CFT, okay? But actually, I'll try and at least comment on how I see potential connections arising even in this setup, okay? So this is some very nice experiments done by Tillman Esslinger's group at ETH, where they place a Bose-Einstein condensate between 2 very highly reflective mirrors, okay? So this is kind of, I mean, the motivation for doing this is that if you put, you know, a Bose-Einstein condensate in an ultra-high finesse optical cavity, all the atoms are in the same quantum state, and so they interact in a very nice way with this electromagnetic field. So you might hope to be able to get to very strong coupling regimes in what's called cavity quantum electrodynamics for studying matter-light interaction, okay? So there's a whole series of beautiful papers coming out of Tillman's group. But this is some recent extension where, in addition to putting these atoms between these mirrors, they also pump this cloud from the side with a transverse laser beam, okay? And so what was predicted theoretically was that if this laser beam intensity is sufficiently strong, the atoms self-organize and form a checkerboard lattice, okay? So this is sometimes referred to as self-organization. And the point is that if you imagine these atoms rearrange themselves to form a crystalline lattice, then they're going to scatter radiation coherently into the cavity. And because these mirrors, even though they're very highly reflective, do leak, the light will leak out of the cavity. So the point is that when you see this self-organization transition, you're going to be able to look at it by just looking at the light that comes out of the cavity, okay? Now, in contrast, in the atomic experiment, you had to expand the cloud to get some insight. Here you're doing kind of novel form of spectroscopy on this cloud just by looking at what comes out of these mirrors, okay? Now, what's rather interesting is that although this looks kind of, you know, a novel kind of transition, what they pointed out in this paper was that, in fact, this self-organization transition has a very straightforward interpretation in terms of an effective spin model, okay? So how to see that there's a spin model floating around in this setup, okay? So the basic idea is that when the atoms absorb a photon from the cavity, okay, so they'll get excited into some higher excited state, but they're also going to receive a momentum kick, okay? So it'll get a kick in that direction, okay? For example, if it absorbs a photon going this way, okay? But when it emits the photon, it could emit it in any direction, but in particular, if it emits it into the cavity, then it will leak out and you will see it, okay? So very crudely speaking, this cloud has two distinct states, one where it's in its k equals 0 ground state, and one state where the atoms have absorbed and emitted a photon, and they're therefore left in an excited motional state, okay? So these two distinct motional states of the condensate correspond to large macroscopic spins, basically, okay? You've got order of 10 to the 5 atoms in this cavity, okay? So if you look what they see, okay, this is increasing this pump power versus what's called the pump cavity detuning. It's basically how your pump frequency relates to the cavity frequency, okay? What you see is that you have this onset at this bright red line where light starts to reach out of the cavity, okay? And that's what we said would happen when the atoms self-organize, okay? But it turns out that this onset is described by a previously elusive transition in the so-called Dickey model, okay? So this is a bunch of two-level systems with some splitting omega naught. These are our motional states of the condensate. There's some effective cavity frequency and some photon field psi, and you have processes where you absorb a photon and flip a spin, okay? And it turns out in this problem there's also some other so-called counter-rotating terms, but we don't need to worry too much about these terms, okay? The basic point is, if you just zoom in on this top bit, when G is sufficiently strong, okay, this model is known to undergo a phase transition, okay? It occurs when G is equal to the square root of omega naught. And this was something that was known in the quantum optics literature. It's known as the superradiance transition, okay? And these spins in this language would undergo a transition from a state where all the spins point down to a magnetized state, okay? Now here, this transition is being simulated by these atoms in a cavity, but what's important is that this is actually a non-equilibrium system, right? Because you're driving it strongly with a laser, light is leaking out of the cavity, and if you look in anywhere in condensed matter physics, if you're looking at transport in some nanoscale device, you always have these driven open systems, okay? So one of the things I want to come on to at the end of the talk in relation to heat transport is that actually I think there's some opportunities for looking at transport properties that you might normally think of in terms of kind of driven open systems, so driven steady states, okay? And I should say as well, I mean, there's actually quite a lot of local interest here in LMU and in Munich in general. I mean, for example, Jan van Delft has been looking at analogous problems to this, where instead of having these two-level systems represented by atoms, you literally have two-level systems formed by superconducting qubits in a microwave resonator, okay? And again, there's very beautiful experiments and proposals to look at non-equilibrium physics in such models, okay? So fine, so let's press on, okay? So why is gauge gravity duality potentially useful? Well, it's useful, actually, let me just go back, just one thing I didn't mention. So the point is that this non-equilibrium physics, I should add, actually also shows up in the formula for the boundary, okay? So this is some effective Hamiltonian, and the transition occurs when G is square root of omega naught. This is actually explicitly shifted by inclusion of cavity decay rate, okay? So in order to understand these experiments, you really do have to think about a non-equilibrium driven steady state, okay? Okay, so back to gauge gravity duality, right? So the point is that, you know, in all of those examples, we're interested in quantum dynamics of a strongly interacting quantum many-body system. And typically, we're also at, I mean, those cold atoms experiments are cold. I mean, these are kind of some of the lowest temperatures in the universe. But in general, if you drive a system out of equilibrium, you might expect heating effects, okay? So the generic problem is a finite temperature problem. And ADS-CFT obviously offers lots of advantages because you reformulate this in a completely different way, where the quantum dynamics is replaced by classical Einstein equations and finite temperature occurs by black hole solutions, okay? So what I think is particularly interesting is that not only can you track the temporal dynamics in these systems, you might be able to extract dynamical phase diagrams, okay? So you're very used to working out a phase diagram of a system, but in principle, you could also work out a dynamical phase diagram asking how does the system respond as a function of the parameters to whatever perturbation you apply, okay? And this kind of thinking might actually shed light on various problems in ADS-CFT, okay? And so one of the things I will talk about is, you know, based on some knowledge of what happens in relation to BCS superconductors, we managed to find a dynamical transition occurring within holographic superfluids. So you can identify certain changes in dynamical response of an ADS black hole, okay? So even if your interest is not in relation to condensed matter physics, actually some of these ideas might still actually help you explore interesting aspects of black hole physics, okay? Okay, and so more generally, just asking the question, you know, what are the organizing principles out of equilibrium? Okay, so let me just kind of briefly summarize then, you know, the kind of things people have looked at on the condensed matter side, and I'll give some explicit examples of these as I go on. Okay, so as I said, you know, people have focused on these very simple protocols known as quantum quenches, where you start with some Hamiltonian with a parameter g, and you abruptly change the parameter to some new g prime, and you ask, how does a system prepared in some state psi g evolve as a function of time? Okay, and there's a very beautiful paper by Pasquale Calabresi and John Cardy, where they asked this question in the context of a 1 + 1 dimensional CFT, because they were interested in whether or not they could tease out some universal dynamics, because if the system evolves under a CFT, you know how to deal with that problem, okay? So John used tricks of boundary conformal field theory to analyze this problem and tease out some universal results that I'll talk about very briefly in a moment, okay? So this has led on to a lot of activity trying to kind of run with this to ask more general questions about what happens in interacting lattice models, okay? Now there, even if the model is integrable, okay, it's actually very challenging to get a handle on non-equilibrium integrable systems, okay? So there's a lot of work done on the Bethe ansatz for looking at thermodynamics, but once you start to look at non-equilibrium problems, this is actually very challenging, okay? So even in 1D, this is a tall order, and I'll just show some transparencies of the kinds of results you can get out for quantum spin chains, okay? Now, what actually motivated this work that I was involved in was actually some known results for quenches in the BCS pairing Hamiltonian. Okay, these were problems that have been motivated on the condensed matter side, largely because of all the advances in cold atomic gases, where you can tune the interactions between your fermions at will. Okay, and in particular, you can start to ask questions: what would happen if you turned on pairing interactions in a BCS superconductor? And so there's a kind of beautiful series of works, in particular by Barankov and Levitov and Boris Spivak. Emil Just-Bashayan moved the whole machinery of integrable models to look at these things. And what a lot of these problems show is absence of thermalization attributed to the role of these conservation laws. Okay, so this is harking back to these 1D experiments we looked at in the cold atomic gases, that actually you see that in general, some of these isolated quantum systems with conservation laws don't thermalize, even at late times, okay? Okay, so let me just kind of summarize how, you know, the results of Cardy and Calabresi point to the fact that actually there may be interesting universal results in far from equilibrium settings, okay? So it's worth commenting on this because it's not actually obvious you can even ask a question about universal results out of equilibrium, right? Because if you drive a system very, very far from equilibrium, you're going to excite lots of excited states. And so maybe it's not even clear that you can get universal results in these far from equilibrium settings, okay? Now, of course, in situations where the system thermalizes at late times, one thing we will see from the ADS-CFT correspondence is that actually the late time dynamics is then effectively traded for a close to equilibrium problem. And so then maybe it's actually much more natural that you can get some universality in the dynamics, okay? I think what I would say is, I mean, here I use universality slightly loosely. I mean just anything that gives you some handle on how a family of different models or problems will behave under non-equilibrium conditions will be a useful step forward, okay? Okay, so what did they show? They said, well, basically, if you start with a system away from a critical point and you quench to a 1D critical point, you can track the time dependence of the one-point functions of a primary field psi, and this decays exponentially to 0 in the late time limit, okay? So that's what you would expect in equilibrium, and that's what happens here, okay? But rather more crucially, you know, this exponential decay is effectively telling you you've got something like a temperature in the problem, okay? And in fact, that's really just set by the initial mass gap in your starting state. You don't start at the critical point, so you have some energy scale in the problem. You quench to the critical point, but when you evolve under the dynamics, your system knows that it's not at the ground state of your equilibrium CFT, okay? The problem is that in general, that dependence is non-universal, okay? It depends on your initial starting conditions. But what you can do is you could, for example, look at ratios of observables with different scaling dimensions. So X here is actually the scaling dimension, okay? So if you looked at ratios of observables, this tau naught parameter parameterizing this non-universal initial condition would drop out of the problem, and then you could get universal asymptotic dynamics in a non-equilibrium setting. Okay? In addition, you know, you can also start to look at behavior of two-point functions, okay? And so there is lots of work on dynamics of entanglement entropy, et cetera, and you know, more generally, just trying to understand the dynamics of multi-point correlation functions in CFT must be quite a complicated problem, okay? And although I know results that connect directly to the 1+1D results, I don't know to what extent these are explored in higher dimensional settings, okay? Okay. So let me just show you then, just very briefly, these kind of developments coming out of integrable models, okay? So we met the Ising model in the first lecture, okay? So this is the Ising model in a transverse field, okay? So the notations differ from my first lecture. These were the notations used in this paper, where the spins now interact along the x direction, but in this transverse direction is now denoted by Z. So this magnetic field acts to destroy the order, okay, because this operator doesn't commute with this, okay? So this has a phase transition between two distinct states depending on the size of this field. And so this work was asking what would happen to the one-point functions and two-point functions if, for example, you performed a quench within the ordered state, okay? And the reason why they're asking questions about what happens in the ordered state is actually it's quite challenging to ask what happens if you cross the transition or if you do it just in the paramagnetic phase, okay? So the point is that if you try and compute these correlation functions, I mean, what we discussed in the first lecture for XXE was that in general you have to fermionize this kind of problem, right? Which means it's a non-local mapping between the spins and the fermions. So even if you do manage to do the recasting, you've still got a very complicated fermionic problem in order to unpack the time dependence of these 1- and 2-point functions, okay? But the basic message is that these things can be teased out, okay? And what you see is that, you know, there's a kind of decay rate as a function of time. This cos parameter this is actually going to give a negative value for this logarithm, so this decays as a function of time. But you see you have this integral over different momentum states, and it turns out that this decay rate, okay, can't be thought of as an effective thermal decay rate. Okay? You pump some energy into the system, and I said very crudely speaking, it's going to decay exponentially as a function of time. But here, when you analyze this as a function of different modes, you see that actually you can't do that, and this thing isn't thermalizing in the sense that you can describe it by a single temperature. So what you have to do is these are basically describing mode-dependent temperatures, okay? And so this is sometimes referred to as the generalized Gibbs ensemble. Let me just turn the light on very briefly. Just saying that instead of your asymptotic state being governed by e to the minus beta h, where h is your Hamiltonian, right? In general, if you're in an integrable model, you're going to have a series of different commuting integrals of motion, and these, in fact, enter into the long-time dynamics, okay? And in particular, there's a recent paper by Fabian Essler pointing out that actually some of these results associated with this generalized Gibbs ensemble actually also apply for dynamics as well, okay, not just static considerations. Okay, and that was just showing you that the exact analytic results also match some direct evaluation of the kind of determinants, okay? So basically they have a fermionic representation and they can compute things numerically, and it agrees with those asymptotic formulae very well, okay? So this is leading to people to try and develop field theory approaches to integrable dynamics, okay? And so that's kind of an ongoing problem in 1D, okay? Now, as I said, what got us started on this problem from the perspective of ADS-CFT was actually some very nice work on this so-called pairing problem where you look at a quench in a BCS superconductor, okay? So these are a bunch of fermions interacting via the BCS Hamiltonian, and what you want to imagine is that you turn the pairing interactions on abruptly, okay? And in fact, in the plots that I will show in a moment, we're actually going to start in the superconducting state and then change this coupling lambda, okay, which will take us from one state with a given gap to another state with a different gap, okay? And we want to try and understand the phase diagram. So what it was pointed out by these authors, and also simultaneously by Emil Just-Bashine and co-workers and Boris Altshuler, was that this problem could be solved exactly, and you could either think of it in terms of writing down a time-dependent BCS wave function, or you could also see it that the problem was still, in some sense, integrable out of equilibrium, okay? So what do you want to focus on? You want to focus on the gap, okay? It's some superconductor. This is some kind of pairing amplitude. And you want to look at the equation of motion governing this gap, okay? And so they managed to tease out equations of motion for this order parameter, okay? And what they demonstrated was that, in general, this system has oscillations, okay? So it doesn't seem so surprising. You start in some superconducting state, you hit it a little bit, it oscillates, okay? In this particular problem, because it's an integrable problem, it turns out to oscillate indefinitely, okay? So they have persistent oscillations. Again, this is very direct reflection of the fact that these models don't necessarily thermalize. It's not even approaching a steady state, okay? So what they did is they went further and put this together into a phase diagram, okay? So this is what I mean by a dynamical phase diagram, that you're looking at the evolution of the order parameter, delta, okay, as a function of your quench protocol, okay? So let me just explain what I mean by that. This ratio here is delta S divided by delta naught. Delta S is your starting gap, so you have some superconductor with some effective interactions, and it corresponds to a certain superconducting order parameter. And then you quench to a final gap, in quotes, meaning immediately following the quench, that's what your system would have had if it was in equilibrium, okay? But it isn't in equilibrium, okay, because you've just driven it, okay? So what you can see is that if you start in an initial gap and you make the final gap, in quotes, small, you're going to be way out here in this phase diagram, okay? So what does that mean? It says, well, basically, you started in a superconductor and you've tried to turn off the interactions and make it non-superconducting. So then what are you going to see? You're going to see that at late times, your order parameter disappears. Okay? So that's what's being plotted. They're plotting the final asymptotic order parameter as a function of this quench strength. Okay? Now, if you don't hit it so hard, okay, what you see is that generically the order parameter doesn't vanish. Okay? So it says that if you don't hit it too violently, it remains superconducting. But what you notice is that there's actually two distinct regimes here. Okay? One is a regime where you have this asymptotic gap, but there's also a regime where you see these persistent oscillations that we saw earlier that come out as being natural solutions to these nonlinear equations of motion. Okay? So they interpreted this as a kind of Landau dephasing transition. Okay? You imagine that you've got some superconducting instability and your individual Cooper pair states can couple to this mode, or your electrons couple to this mode. And so basically what's happening is that your oscillations are ultimately dephased by coupling to this collective mode. Okay? So it's something that happens in some collisionless regime, but because you've got some collective excitation that your system can interact with, you can get some dephasing phenomena. Okay? And so this is what they see in this exactly solvable problem. Okay? And in particular, what they see in this regime is an overdamped approach or beg your pardon, an underdamped approach to this asymptotic gap, where here they see an overdamped approach. Okay? And so what we're going to want to try and do is to ask whether or not we would see such behavior if we did this for a holographic superfluid. Okay? And there was a kind of large number of reasons to do this, because you can imagine that here we've got these persistent oscillations, but presumably in a realistic superconductor, you're not going to see persistent oscillations to late times, okay? So if you've got any external environment or any other forms of scattering in the problem that are omitted in this BCS Hamiltonian, then you're not going to see persistent oscillations. But on the other hand, if you want to try and get a quantitative handle on such problems, it then becomes difficult to treat it analytically, okay? Now, in a sense, you know, within ADS-CFT, all of these features are incorporated, albeit for a particular class of models, okay? Okay, so this was just to show you just a little bit more detail about the predictions. One thing you can do is, I mean, in the first lecture we went from spins to fermions, okay? This is an example where it's actually interesting to go the other way. They start with a bunch of electrons, but they use these so-called Anderson pseudospins. And the point is that in this representation, okay, what they're basically doing is they're changing the coupling in this effective magnetic description. And so you can imagine trying to solve the semi-classical spin dynamics for this problem, and that's basically how they can get at this diagram. And you see that indeed, depending where you are in parameter space, you might have some damped oscillations or some overdamped approach to this asymptotic state with particular prefactors, okay? So what we want to try and do then is see if we can get that for a holographic superfluid. And just before moving on to that, I just wanted to say that, you know, in the ADS-CFT literature, I mean, there is a huge literature now of people looking at far from equilibrium holographic problems within the context of thermalization, strongly coupled gauge theories, okay? What's a little bit different is that in a lot of those papers, people are interested in what happens if you deform the metric in a time-dependent fashion. Okay? So it's not necessarily that the physics is any different, but the way of going about it is a tiny little bit different than what I will describe later. As a condensed matter theorist, I'm imagining, you know, the ADS-CFT correspondence is useful if you focus on the boundary theory as being your system and use the duality to extract the temporal dynamics. Okay? So what that means is that most of the things that I will do in my boundary theory as a function of time, I will just do exclusively in the boundary theory. This will then induce some change in the metric, and then I'll follow that as a function of time. Okay? So rather than actually making perturbations directly on the metric in the interior of ADS, I want to somehow focus on time-dependent phenomena in the boundary and do everything from the perspective of the boundary theory. Okay? But nonetheless, there's quite a lot of parallels to these problems, okay? And in particular, in this paper, they managed to make contact directly with the results of Cardi and Calabresi, okay? So basically, the results of Cardi and Calabresi are valid for an arbitrary CFT, and there's various tricks you can use that in the limit of large scaling dimensions, you can use various properties of ADS-CFT to recast it as essentially a kind of geometrical optics type problem. And so they were able to, I think, make contact in this limit of large scaling dimensions. Okay, so let's start with what we actually do then, right? So what we want to try and do then is start with some concrete holographic model in this so-called bottom-up approach, okay? So just to remind the condensed matter physicists, I mean, basically you've got two distinct approaches within this kind of ADS-CFT type setting. One is you specify the action in the interior of ADS space-time and try to understand how the system behaves on the boundary, okay? The other approach, in the kind of top-down approach, you would try and derive things microscopically from some string theory in some higher dimension and compactify. Actually, from the point of view of condensed matter physics, the bottom-up approach is actually rather natural, okay? Because you're basically positing certain actions based on symmetry, okay? Here, you're trying to describe some holographic superfluid, so you want some charge scalar field. You're going to couple this to electromagnetism and gravity, and therefore this looks like the kinds of problems you would write down in condensed matter physics, okay? The problem is you don't know what the boundary theory is corresponding to this, okay? But nonetheless, you can ask how does the order parameter evolve as a function of time in this kind of setup, and in particular you can see connections then to the phase diagram that I showed earlier in relation to a BCS superconductor, okay? So what's known then about this model? Basically, if you're at high temperatures, this field psi is 0, and you're described by the so-called Reisner-Nordstrom black holes, solutions of Einstein-Maxwell, okay? Below a critical temperature, these black holes become unstable, and you start to develop solution with scalar hair. So psi becomes non-zero, and so this corresponds to the onset of spontaneous global U1 symmetry breaking in the boundary theory, okay? So we have a system that in equilibrium, thanks to Sean and Steve Gubser and co-workers, that exhibits a broken order parameter on the boundary, okay? And so now what we can do is we can say, well, if we kick this and we start in a superconducting state, what happens as a function of time, okay? Okay, so this was actually looked at by some very nice work actually before us, okay, also in the context of non-equilibrium ADS-CFT, where what they said is, they said, well, okay, I mean, let's start below TC, okay, but let's start in the Reisner-Nordstrom black hole corresponding to being in the normal state, okay? Still a solution of the Einstein equations, but it's not going to be a stable solution, okay? So if you then start in this normal state below TC, okay, this is like starting in a supercooled liquid, okay? And so what they do is they then kick this ball off the top of this hill and ask how does it roll down as a function of time, okay? And so the way they do this is very natural. So you have your ADS boundary, which from a condensed matter point of view is where your superfluid's living, and you have this extra coordinate Z that goes into the interior of ADS space-time, okay? And so at t equals 0, you have some initial surface corresponding to this Reisner-Nordstrom black hole, and they perturb it in a particular way, okay? And so the way they perturb it is you say, well, you have this field psi that lives in the interior of ADS space-time. It's a function of time and Z. You're going to expand this close to the boundary, okay? And as all the string theorists will know, usually with these kinds of expansions, you have an interpretation that one of these coefficients you can think of as source field for a corresponding expectation value, okay? So this psi is somehow encoding the physics of this superconducting order parameter. So this psi2 will correspond to the order parameter in the boundary theory, and this is like a source field for that order parameter, okay? So if it was a magnet, this would be like a magnetic field coupling to the magnetization, okay? So what they do is they just kind of expand this and just recast it, and they just choose a particular Gaussian perturbation just to kick them off the hill, okay? But really what they want to do is to monitor the evolution of this psi2 following such a protocol, okay? And so what they see is that, you know, depending what temperature regime they start in, if they start above Tc in the normal state, you wind up at late times in the normal state. So the order parameter disappears at late times, okay? On the other hand, if you're actually below Tc, then your superconducting order parameter grows as a function of time, and they're able to extract these relaxation rates as a function of temperature through this system, okay? Sorry, I'll just get some water, okay? So that leaves a whole bunch of questions, okay, which I've just summarized there. We didn't actually get close, I would say, to even answering all of these questions, but, you know, just a huge number of questions, right? So the first thing then is that if you go back to those figures, right, there was no visible damping, no visible oscillations, okay? We saw these oscillations in this Barankov-Levitov problem. But if you imagine you look at this, I mean, there could be a whole variety of reasons why you wouldn't see that, right? I mean, one, it's a large N theory. Also, you've got a large number of gapless degrees of freedom. Also, problems in ADS-CFT thermalize very rapidly. So there could be a whole host of reasons why you wouldn't see such things, okay? So what we wanted to do was just say, well, okay, look, I mean, if we just try to flesh out what you might think of as a dynamical phase diagram, could we just see anything interesting in this kind of system and try and map it out more systematically? And in particular, to only do those quenches on the boundary itself, okay? So fine, so this is the setup. So we have the CFT that we're interested in, and we're going to apply pulse on this boundary theory, and we're also going to solve the same homogeneous isotropic Einstein equations. I should say that actually we're making an assumption that the subsequent evolution is homogeneous, okay? Now, I did stress at the beginning that actually, you know, generically, if you quench some system, you might expect inhomogeneities to form, okay? What we suspect is that actually, even if you were to include such inhomogeneities, as you will see, our results for the homogeneous case are described by quasi-normal modes, so that at least if your system thermalizes at late times, the dynamics, the early time dynamics may well be different because of the formation of inhomogeneities, but presumably your late time dynamics is still described by an equilibrium calculation, okay? So that's somehow the logic. But in any case, you've got to start somewhere, so that's the assumption we make, and then we ask how does the time dynamics evolve, okay? And so if you take this order parameter then, right, this is like a source field for this corresponding order parameter, we just apply a little Gaussian pulse, okay? So it's not an abrupt quench, okay? This is something Toby Wiseman's been working on recently, so he's managed to get things up and running so he can do rapid quenches, basically, okay? But this is just some delta function quench, so we have some amplitude and some time scale, and we just set these this time scale just for simplicity to just half the initial chemical potential, okay? And the initial temperature we just take as half Tc, okay? So there's nothing deep in that choice of parameters. And then we ask what happens then if we change this quench strength, okay? So you see that indeed, if we hit the system very hard, the final order parameter disappears, but if we don't hit it so hard, we have some non-vanishing order parameter late times, okay? But rather crucially, we also see this change in dynamics at an intermediate quench strength, okay? And so you can get a little bit more insight into that just by looking at the plots, okay? So what I'm showing is 3 different plots starting for different parameters, okay? For the same parameters, but just quenching by increasing amounts, okay? So as I said, if you do a very hard quench, okay, you see that you asymptote to this normal state at late times, whereas for intermediate strengths, you wind up at some finite value. It's a little bit hard to see on this diagram, but that's non-vanishing at late times, okay? What's interesting is the fact that here you see an oscillation for weak quench strengths, which you don't see once you exceed a critical value. Okay? So the late time dynamics is changing from a damped oscillatory behavior here to an over-damped approach to this superconducting state at late times. Okay? And as I'll show in a minute, the asymptotics of this approach can all be understood within a close to equilibrium calculation about one of these black hole solutions. Okay? And this is quite interesting from a condensed matter point of view, because you can basically recast this far from equilibrium problem as an equilibrium problem at late times, okay? As long as you understand how to describe the quasi-normal modes of these black holes, okay? So let me just demonstrate, given all of the discussion I had about kind of systems not thermalizing, one of the things all of my string theory colleagues tell me is that, ADS-CFT models, by construction, thermalize, okay? And I think generically that is clearly true, okay? I still wonder, and I believe there's still an open problem to actually understand how the results within ADS-CFT match results coming out of low-dimensional integrable models, because there's a huge amount of evidence that in general these low-dimensional models don't thermalize. Okay, could be an issue with the large n limit. It could be that the role of conservation laws is furnished rather differently. There could be a whole host of reasons, okay? But on the other hand, there is a strong connection between methods of ADS-CFT and conventional CFT, okay? Also, black holes in 2+1 dimensions are rather different, so that's another possible reason why they might not match up, okay? But let me just return. I mean, this is, I didn't say it, but we're looking at some 3+1 dimensional system, but because we assume that the evolution is homogeneous, it's actually described by 1+1 dimensional partial differential equations, okay? And so here I'm just showing a plot of this quench strength versus the final temperature of your black hole, and what you see is that stronger you hit it, the higher the temperature is of this black hole state, okay? So what that suggests then is that if you plot that dynamical phase diagram as a function of delta, not in terms of how hard you hit it, but in terms of the asymptotic temperature of your final state black holes, then what you see is this phase diagram collapses onto the equilibrium phase diagram, okay, for the holographic superfluid. What it says is you basically just invented a very fancy protocol for heating up your equilibrium system. You just hit it very violently, the system gets hot, and you're interrogating this equilibrium phase diagram. However, there's still this dynamical transition occurring within the superfluid phase. And so now, instead of occurring at a critical value of this quench strength, it now occurs at a critical temperature, okay? So what it says is that within this holographic context, there is an emergent temperature scale that's below the onset of Tc, okay? That you wouldn't see by an equilibrium calculation, but you do see it if you perturb these systems, okay? Okay, so then this can all be understood in terms of quasi-normal modes, basically saying you want to look at the vibrations of this black hole and ask how do these excitation frequencies change as a function of temperature, okay? And the basic point is that if you look at these modes as a function of temperature, this is starting in the normal state. You have two modes here, okay, that are related by omega goes to minus omega star because you have time reversal invariance. These modes, because you're in the normal state, okay, this final order parameter is 0, when you take the modulus as we've done here, the potentially oscillatory components drop out and you get an overdamped approach to the normal state, okay? So it looks like you're going to get oscillations, but in this quantity you don't, and so you get this overdamped approach to a normal state, okay? So what happens as a function of temperature is these modes hit the origin at Tc, okay? This corresponds to the onset of spontaneous symmetry breaking, and as you lower the temperature, one of these modes remains at the origin and one descends down, okay? So heuristically, this is reflecting the onset of spontaneous symmetry breaking, okay? You go into some state described by a Mexican hat potential, okay? So you have some gapless Nambu-Goldstone boson and you have some massive amplitude mode, okay? And so what we're seeing is that indeed we see a massless mode that remains pinned to the origin, but we also see a massive mode that comes descending down in the imaginary axis, okay? So this corresponds to the onset of spontaneous symmetry breaking, okay? But rather crucially, as the temperature is lowered and this comes down further in temperature, we see some additional modes come up in the complex plane and they cross at a critical T star that corresponds to the T star we saw earlier, okay? So there is a dynamical phase transition occurring within this holographic superfluid where these modes change roles, okay? And so what I just want to show you is, it's not to indicate that you might be able to see this directly in an experiment, but there's very close parallels to very beautiful experiments done in the group of Emmanuel Bloch here in Munich, okay? So what's being shown here is that you're going from a Mott insulator to a superfluid, okay? We met this in the context of the Bose-Hubbard model, and that's what's being looked at here. You go through this transition described by a relativistic Landau to the 4 theory, and you go into this superfluid phase, okay? So what you expect from this picture is that you should be able to see this massive amplitude mode, okay? But in order to see this, you have to excite your system, okay? And so what's done is the coupling J is modulated by a little amount at some frequency nu, and then what they do is they look at the temperature of their gas, okay? So they have a real space imaging way of doing this to kind of monitor the temperature of their Bose-Hubbard model. And what you see is that as you change this frequency, okay, or let me state it differently, as you tune these hoppings, okay, this corresponds to point 1, this corresponds to point 2, this corresponds to point 3. As you change your interactions in your Bose-Hubbard model and you interrogate at different places, you see that the frequency which you need to apply changes, okay? You get a spectral feature occurring for a different critical oscillation frequency, okay? So what that tells you is you're probing a gapped mode in this superfluid, okay? You're seeing, in quotes, the Higgs mode, okay, or the amplitude mode, corresponding to this spontaneous symmetry breaking, okay? So this is another example of seeing spontaneous symmetry breaking. You're not necessarily doing a kind of rapid quench into a broken symmetry state, but you're interrogating the excitation spectrum of this superfluid. And so if I just go back to this plot, you know, in a sense, what these quasi-normal modes are telling you is that you have some excitations in your system with frequencies that play a role in determining your dynamical response. So you might not have a simple quasi-particle picture that you can think of, but you can think in terms of these black hole modes as providing a kind of proxy for quasi-particles in your boundary theory, okay? And so one interesting question is whether or not this dynamical phase transition occurring within the superfluid state could occur in a condensed matter system, okay? And that's not clear because it's hard to compute these modes. There could be all sorts of differences in the pole structure, but one thing that's just worth pointing out is that this pole structure is just what you would expect on rather general grounds if you have time reversal invariance and spontaneous symmetry breaking, okay? So there's at least a chance that it could occur in some other problems, okay? So, yeah?
When you looked at the long-time approach of the order parameter asymptotic value
Yeah.
after your quench, was the rate solely determined by the temperature itself, or did it also depend on other parameters?
Very good. So in general, so let's go back. So we chose a specific value, for example, of the parameter. There's a parameter Q, which is like the charge in this theory. You shouldn't necessarily think of it as the charge of a Cooper pair, because actually it could also involve bilinears of bosons, or even just bosons directly. So in general, the quasi-normal modes depend on the parameters in your system and temperature by virtue of the fact that they move around as a function of temperature. So in this case, what we see is, for example, an overdamped approach at late times to the normal state with a particular damping frequency that comes from these quasi-normal modes, okay? So What I don't have a clear handle on is what the analytical forms of those modes are, to then put it back and say this is how it depends on explicitly on temperature and parameters. Okay, so these quasi-normal mode calculations were done by Julian Sonner. Also, Toby Wiseman also managed to tease them out directly from the nonlinear dynamics. Okay. They're obviously, I mean, you know, you've got a large number of fields in this problem, and so it's a kind of intensive numerical problem to kind of get these quasi-normal modes out. Actually, Julian managed to do a fair bit analytically, actually, in manipulating these equations to get them in a compact gauge invariant form that you could get a handle on. Okay, so that's actually one of the things we would like to understand in more general, to try and relate things back, if we can, to Barankov-Levitov. I don't know whether it's so easy to do it because, you know, they are different systems. But on the other hand, you know, you have an extra tool that to organize the dynamics in a system that is solvable, but not integrable in the 1 + 1D sense as we usually understand it. Okay, so that doesn't quite answer your question, but that's how we understand it. Okay, so fine. So are there any more questions? Because I'm going to switch gears slightly to the work that we're doing now, which is kind of ongoing unpublished work, but it's relating to this question of driven steady states. So are there any questions? Okay. Okay, so fine. So what I kind of showed you in the first part is that, you know, in these holographic examples, you do see thermalization late times, and so you can, if you solve the full Einstein equations, you get the full temporal dynamics. If you just want asymptotics, you can get this by quasi-normal modes. One thing I was very interested in is just trying to understand how you could understand thermalization from a somewhat more condensed matter perspective. Okay, and this was just a cartoon, just to kind of illustrate how a condensed matter physicist would normally think about thermalization. Okay, and actually it's not even a condensed matter physics way of looking at it. I just mean in undergraduate thermodynamics, if you ask are two systems in thermal equilibrium, you join them together and ask if heat flows. Okay, so then that got me thinking about this problem, and actually, you know, this hasn't really been looked at properly in either the condensed matter literature or I think in the ADS-CFT literature. And I think part of the reason is actually it's not that easy to take two strongly interacting quantum systems and just glue them together in this kind of primitive fashion. Okay? But nonetheless, you can ask the question. And I was quite struck because actually there was some very beautiful work that came out by Benjamin Doyon and Denis Bernard, okay, which pointed out something rather cute that I'd missed when I was originally thinking about these problems, okay? So what had I missed? I mean, basically, it's just relatively dumb, right? If you take two systems together, they thermalize, okay? And so then the question is, do you see anything interesting and universal in that setup if they just exchange energy and equilibrate? Okay. Yeah? So two isolated systems. Just take two isolated systems and bring them together. Sorry? Well, so this is what I was naively imagining. If you've got two blocks of material at two different temperatures and you just bring them together, they're going to... Okay, so let me state what conclusion these authors came to, which was different than I'd originally thought. And it's just pointing out that actually if you have two systems that are infinitely large, two isolated systems, but infinitely large, and you bring them together, then they act like their own heat baths, okay? So even though they're isolated, if you bring this into contact with this and join them together, okay, it's kind of local quench instead of a global quench now, then what they predicted that actually you get a steady state heat flow across this interface, okay? So let me show you what they state, and then this also crops up in numerics, okay? So if you look at this problem, what they come to the conclusion is that if you look at times, okay, that are much, much less than L over V, okay, so you're imagining joining two critical systems as a characteristic velocity in the problem, then they say that if you somehow look at a scaling limit where you take this system size to be very, very large, okay, and look at times that are much, much shorter than L over V, then you get a steady state heat current, which is determined by the temperature of your left reservoir, temperature of your right, with some universal coefficient that doesn't depend on this effective speed of light. Okay? Now, why is this interesting? Well, it's interesting from a whole variety of points of view. One is that this is not a close to equilibrium result. Okay? It depends on t left squared minus t right squared. Okay? It's a far from equilibrium result. Also, it is universal, okay? You know, note if you looked at the central charge by looking at the corrections to the ground state energy, this normally involves the effective velocity of light, okay? So this is a non-universal result, a universal result that shows up in a non-equilibrium setting, okay? It's related to things you know, okay? So what I'm interested in now is actually, can you tease this out of ADS-CFT? Okay, and the answer is yes. But more crucially, can you generalize it? Okay, and that's what we're currently trying to sort out now. Okay, because there was a conjecture in the original paper as to how this would generalize into higher D. But the problem is that in general, you don't have calculational tools to compute this. Okay, so let me just comment on how you can understand this result. Okay, you can actually understand it from quite a few different vantage points, actually. So, for example, if you were to just re-express this not in terms of T left and T right, but in terms of some average temperature and a temperature difference. So just put this at T plus delta T and the other one at T minus delta T, and then just expand that out. Then this coefficient is also the coefficient that must correspond to linear response thermal conductance in this channel, okay? And so this has a very simple form involving temperature, okay? And in particular, this pi over 3, okay, I'll come back to, is related to the pi over 3 that crops up in the Wiedemann-Franz law, okay? So even though you don't have quasi-particles, okay, this, in this 1 plus 1D setting, there's still a kind of, you know, quasi-particle-like character to the resulting formula, okay? So this unit of quantum thermal conductance depends on temperature, okay? So it's not just some universal number, it depends on the temperature you work at, which is not so surprising because you're asking about energy transport, okay? But this was previously noted in work by these authors, including Dima Komenitsky, and one way to kind of just get a handle on this value is just if you assumed the Wiedemann-Franz law works, okay, and just set E squared, just set the conductance to E squared upon H, then you will find a natural unit for thermal conductance that has the same dependence, okay? So it's just it's not to prove Wiedemann-Franz holds, it's just to say that it's not an unnatural unit just from standard things you will have met relating thermal conductivity to electrical conductivity, okay? And this had also been seen in connection with the conformal anomaly quite a few years ago by these authors, okay? So fine, so this was just to demonstrate that this conductance can be observed experimentally, okay? So this is some experiments where you have something like a reservoir of phonons, okay? You have some metallic contact in place that heats up your sample, and so your phonons propagate out along 4 wires, okay? And when you analyze the vibrations in these 1D wires, there's 4 low energy phonons per wire, and so you expect your conductance to saturate at 16 times this conductance quantum, okay? And indeed, that's what they see, okay? So this thing is a measurable quantity, okay? And what would be nice is to be able to get deeper insights into both this result, but as I said, also generalize it, okay? So let me see how I'm doing for time, okay? I may skip this and we can, well, okay, let me just give a heuristic derivation of this because it is useful, right? If you look in those experimental papers, okay, how they think about heat transport, they're obviously not doing anything with fancy CFTs. They're just saying, look, I mean, you've got a left lead that's some temperature reservoir, a right lead that's some temperature reservoir. Actually, let me just clarify something. Again, in the setup of Denis Bernard and Doyon, they're joining together 2 isolated systems in this local quench. That's not the same, a priori, as driving the system with a heat gradient. Okay, you're not actually applying a T left and a T right. However, I suspect the two problems are the same, because if in this local quench the left side acts like a left reservoir and the right as a right reservoir, there must be a connection between just this isolated local quench and the results you would get in a driven steady state experiment. Okay? So what they say is, they say, well, okay, imagine you've just got two reservoirs, one on the left, one on the right, with some Bose distribution. You're transporting energy at some rate V, then the heat flow between these two different reservoirs, okay, you can get at by just thinking in the first instance just about a single mode, okay? In the previous experiments we needed to consider more, but if you just consider a single mode with linear velocity Vk and do this integral over the Bose distribution function, then you essentially get the result that I showed, okay? And if you interpret this, what it says is a CFT has an effective number of degrees of freedom which are transported in this heat flow, okay? So with the perspective of kind of higher dimensional generalizations in ADS CFT, you might imagine that, you know, some of the anomalies that describe high dimensional CFT, such as the A parameter or F parameter or the various other parameters, might play a role in replacing the central charge in terms of counting the effective numbers of degrees of freedom that are relevant to heat transport. Okay? And again, just to come back, I mean, that was also a point that Subir was making close to equilibrium, right? There's a lot of parameters describing these 2+1 and 3+1 CFTs that should enter physical quantities for current, okay? So one possibility is maybe some of these parameters also enter into far from equilibrium settings, okay? We don't know that yet in higher D, but that's what we're trying to explore, okay? Okay, so maybe I'll skip this and come back to it, okay, depending on the time. So we finish at past, don't we? Okay. So this was just to try and give a kind of heuristic picture of this T-squared dependence and how it might connect to high-dimensional generalizations. The basic point is that the energy density of a CFT in D dimensions goes as T to the D plus 1, okay? So this difference of T left squared minus T right squared is the same as the energy density of a CFT, and so you know from the theory of black body radiation that the internal energy density in 3+1 dimensions goes as T to the 4th. So this is just the analog of that in 1+1 dimensions, okay? And these quantities, let me skip that, play a role also in the kind of formal aspects of ADS CFT, okay? So this is, you know, the kind of very famous results for entropy in SUN Yang-Mills, okay, and pointing out the fact that actually this coefficient, it's TQ because we're looking at entropy density, not internal energy density, differs from the weak coupling result by this kind of magical factor of 3/4, okay. So these numbers are of relevance to ADS CFT, and there is the possibility that these kinds of numbers are entering all over the place in condensed matter applications, and the question is just to zoom in on what those applications are, okay? Okay, so let me just comment on something that I had to rush over quite a lot in the lectures I gave last week. One of the very nice things that also came out of this work is that not only can you work out the average current, you can also work out the fluctuations as well, okay? So if you imagine that in any quantum system there's an average heat flow, okay? In general, there's some fluctuations around this flow, and in this 1D case, you can work out an expression for a generating function for all of these moments, okay? So let me unpack this. This Q is the amount of heat transported over the interface in a certain interval of time. This lambda is sometimes referred to as the counting parameter, okay? And if you construct this generating function, then through derivatives with respect to lambda, you can tease out both the average heat current and the fluctuations, but also all higher moments, okay? So this is the exact result for that, and you see that if you expand it in powers of lambda, okay, I denote Z equals I lambda, then these coefficients are average current, first moment, second, etc., okay? Now, what's interesting is that somehow behind these results is a kind of hidden Poisson process, right? if you look at this expression, how it drops out from the exact solution, this is some integral involving some kind of Boltzmann weight. There's some kind of thermal activation of particles in quotes, which are giving you some kind of stochastic interpretation of this heat flow process between CFTs, okay? At least in 1+1 dimensions, okay? And this may in turn come back to the fact that, you know, you have effectively some black body radiation. We all know that black body radiation can be described in quanta, and so there may in fact be a kind of particle-like picture behind this, okay? So this was just to point out that, you know, there's kind of huge number of ways to potentially generalize these results, okay? This belongs to a class of literature known as full counting statistics, okay? So this was looked at quite a lot in the mesoscopics community. You're imagining that you've got some transport of either charge or heat across an interface, and in general, you know, this will be communicated by some lumps, okay? So electrons are discrete objects, okay? So there's a question about how you monitor this discreteness of the charge, okay? And it shows up very naturally in the noise measurements, whereas it doesn't show up in the average flow because they could just be traveling at twice the rate, okay, with half the charge, right? So this is quite important because actually, you know, you can get a handle on the charge of your carriers, for example, right? And so one of the famous applications of this was determining the fractional charge of quasi-particles in the quantum Hall state, okay? So if you're so here you have some quantum Hall state which on average has filling factor 2/3, but you apply some little gate voltage to deplete this, and so this is actually some state at filling factor 1/3. The quasi-particles that tunnel through this constriction have charge 1/3, and you'd like to be able to see this fractional charge, okay? And so measuring these noise correlations, okay, in this process, you can actually determine the fractional charge of these carriers. And you see, it differs quite a lot than assuming the charge is E from the experimental result, okay? So the noise results are actually genuinely useful, and so these heat flow results are kind of pointing the way that you might be able to do a much better treatment of understanding heat flow in strongly correlated systems, okay? Another thing I should just mention as well, and I actually noticed one of our members in our audience, Stefan Karain, has done actually some very nice recent work on this, and actually is going to be more of an expert than I am in this area. But one general question is, are there interesting relationships that hold in non-equilibrium systems, okay, that mirror, you know, things like the fluctuation-dissipation relation close to equilibrium, okay? So if you look at this formula for this generating function for heat flow, it has a certain symmetry under the lambda going to minus I lambda, okay? And if you remember from the definition, let me just go back, right? You know, this is kind of like either adding or subtracting charge, okay? So this relation is a little bit like the kinds of relations you look at in non-equilibrium systems, such as if you have some process that does a certain amount of work on a system, a non-equilibrium process, what's the relationship between the probability for doing a certain amount of work W and a certain amount minus W, okay? Now, even in a non-equilibrium context, there's been various relations derived that under certain circumstances, these can be related to equilibrium quantities, right? So this is the work done, or this is the change in the free energy between the initial and final states. And so it's saying the probability of having done work in the forward direction relative to the probability of having done work minus W in the reverse direction is related by the work that you are asking about and the equilibrium free energy, okay? So you're starting to relate non-equilibrium processes to equilibrium concepts. Now, in general, for interacting quantum systems, teasing out such general relations are going to be very hard, okay? And so one possibility is that this ADS-CFT correspondence might be quite useful in extracting non-equilibrium fluctuation relations, okay? Okay, so I've still got a few minutes. I mean, are there any questions, actually, before I carry on? Because I can always stop. Are there any questions at this stage? Okay, so this was just to demonstrate that these results for the average heat flow actually have now been seen numerically, okay? So in particular, we met this anisotropic Heisenberg model in my first lecture, okay? We said that if you tune delta to be between -1 and 1, this describes a critical system, okay? And if you look at that and join them together, then this is some recent numerical experiments done by Karash in the group of Joel Moore at Berkeley, where they join these two spin chains together and they monitor the average heat flow at the interface, and you see that at late times, this approaches a steady state, okay? Now, the value of the current depends on whether they have what their left and right temperatures are, okay? So this is for T left is 0.5 and varying T right, but we know this formula obviously involves T left and T right. So you're seeing the onset of this steady state current, okay? And in particular, what they can also do is, because they have a model that they're solving numerically, not analytically, they can also add integrability destroying perturbations, okay? So this they call dimerization. This is just modulating the exchange coupling from site to site, okay? So that generically breaks integrability. You can also add a staggered magnetic field that alternates from sign. This will also break the integrability. And what they see is that even in the presence of these perturbations, they can also see this non-equilibrium steady state, okay? Now, there are circumstances where this steady state appears to differ, but it's rather robust, okay? So this is a kind of clear statement that these CFT results can have validity out of equilibrium and in non-integrable situations that you wouldn't have a priori been able to see, okay? So the CFT results provide important benchmarks, okay? And this is just to show a little bit more data. If you look at this for various temperatures, but as a function of T right, okay, what you can see is that they're just basically the same curve, but they're just shifted, right? So it says that your average energy current is a function of T left minus a function of T right, okay? Now, you know, kind of heuristically, that's not unreasonable because you've got two 1D CFTs, you know, there's a kind of, I should state something. So when I say left and right, let me just be clear, this isn't a chiral system, right? I don't mean left and right movers, okay? So that caused some confusion before. I meant to change it to T hot and T cold, okay? So we have a left and a right system, right? And in 1 plus 1D, we also have factorization to left and right movers, okay? Now, the conjecture that Benjamin had for higher dimensions is that this also has a similar left-right factorization in the physical sense, but obviously to think about this in terms of scattering processes is obviously more complicated in the higher dimensional case, okay? Because you can't just think in terms of left and right movers, right? Nonetheless, here you see it, and I should state actually that this factorization was actually conjectured by Benjamin. I think he actually included this in one of his talks actually before it was published, okay? So, okay, and so in addition, in these numerical simulations, they can also see a crossover from the low temperature behavior to the high temperature behavior. And remember, because we're in a lattice model, we also have non-universal aspects associated with the fact that we have a cutoff, okay? So in general, this T-squared dependence will evolve in a lattice model at high temperatures, but nonetheless, you're seeing that the data agrees very well over the interval that it should agree in the lattice model, okay? So fine. So let me skip that because that's just about integrability. There's some conjecture that somehow, if you read Joel's paper, that somehow the existence of this finite heat current is associated to the existence of a Drude weight in the 2-point function of the current, okay? And so the place where he sees the steady state disappear corresponds to the place where he can't see any Drude weight in this 2-point function, okay? Okay, so ADS-CFT. So how can you start to imagine tackling such problems in ADS-CFT? Well, you know that the stress tensor on the boundary is related to the metric, okay? And so, in principle, this is very nice for condensed matter physicists because what it means is you can look at this problem in pure gravity, okay? You don't need any matter fields, you don't need any gauge fields. Just look at it in the simplest example of ADS-CFT and try to get a handle on what's going on, okay? So there's various ways you could imagine doing that, okay, and hopefully we'll try and do some of these things, okay. Probably the most natural from tying it to the work that I described in 1D is probably the most difficult, actually, right? Because you could imagine a situation where you take two black hole solutions at two different temperatures, join them together, and ask how does it evolve as a function of time, okay? Now, it's probably hard to do some of these computations analytically. I think there may be ways to do it, but this is clearly something that in the first instance you might try numerically, and it might actually be very hard, okay? You could also imagine setting up a driven steady state, okay, where you adjust the boundary conditions on the left-hand side and you try to see if there's a heat current, okay? The third approach, which is what we've tried so far and actually seems to make contact with these results, at least in 1D, is that you can ask, are there situations where you develop spontaneous heat currents in this boundary theory, i.e., are there steady-state solutions of the Einstein equations that actually give you some heat flow on the boundary, okay? And so one very simple way to try and look at this is that if you just think about kind of general considerations of energy momentum conservation within CFT, okay, if you, or just in field theory first of all, right, if you assume you have stationary heat flow, i.e. the derivative of this component is 0, it automatically means that your Txx has to vanish, and so you have constant pressure, okay? And so if you're in a CFT, okay, this constant pressure turns out to mean that you have a vanishing derivative of the internal energy density because this pressure is related to the internal energy density in the way it is for Boltzmann, okay? So what it says is we're looking for stationary homogeneous solutions of these Einstein equations, which nonetheless are not in local thermal equilibrium because we have a flow. Yeah.
You have a black hole in the solution?
We will next, yeah. So that's the question, right? So it turns out that if you look at the problem in 1+1D, okay, there is a unique solution for what those black holes are, okay? So this was a nice argument due to Conrad Charm, okay? So if you look for these solutions, right, then it turns out that they're basically boosted ADS black holes, okay? So there's some boost parameter eta, T is your unboosted temperature, okay? L is your ADS radius. And so if you work out the expectation value of the energy momentum tensor on the boundary corresponding to this solution, okay, then you can recast this in terms of the central charge, and what you find is that the component of the stress tensor, the Tx component, okay, that you need for heat flow, has this form that it's T squared times e to the 2 eta minus T squared times e to the minus 2 eta, okay? So what it means is that if you identify T left and T right with a boosted temperature, right? So you imagine you run in one direction, it means that one side is going to be hotter than the left via this relation, then you recover this formula in 1D, okay? So what are the things we're trying to do now, right? So the first is, what this is telling you is, you ought to be able to derive this answer by Lorentz transformations, okay? Myself and Benjamin did this on the blackboard and we haven't written it up, and it looks like you can tease this out. The thing that we need to check is whether or not we also get the fluctuations correct in this state, okay? Because if we don't, then there's a problem in matching these things. But if the fluctuations in this state match what come out of the ADS-CFT calculations, then what it says is that you've been able to identify the correct steady, non-equilibrium steady-state solution that matches the CFT predictions. And now the question is it possible to generalize some of these ideas into higher D and see if there's any universal results for heat flow and heat flow fluctuations? Okay? And so one of the ideas that people were quite keen to kind of present when I was chatting about this last week is that some of these results ought to be derivable also within hydrodynamics as well, right? Because essentially you're also looking at transport coefficients. Okay, so that's kind of a program for the future. And so then I'll just end here saying, you know, there's quite a lot of potential, I think, for looking at non-equilibrium processes in ADS-CFT. And, you know, these are just kind of simple entry points that we're trying to link up to condensed matter audience. So, okay. Everyone need a copy? No, so that's what we're looking at. So the question is that the solution to, so let's draw it, right? So what's being said roughly is that if you have two blocks of material like this, right, then this is at T left, this is at T right, okay? You can boost in one direction, and there is a generalization of that formula. So the first thing is it unique, okay? It looks like it's not unique, okay, but we need to check this. And you can first of all exclude rotating black hole solutions. So as long as you're not on some compact spatial direction, we can neglect those. So there are a family of black holes in higher dimensions that would correspond to the boost solution. The question is, does that boost solution correspond to having a steady state heat flow per unit area of a system at T left and a system at T right, okay? And that's what we're trying to check. So possible things to do are to do free field computations where you can check whether or not your answers match, try to look at the non-equilibrium density matrix. The reason it's a little bit more complicated is that, you know, in 1D, we not only have this kind of factorization to left and right side, but we also have factorization to left and right movers, literally. Here, it's obviously a little bit more complicated. Okay? Now, if you wanted me to guess, I mean, you know, if you imagine this was like a kind of black plate, okay, radiating energy, you know, kind of crudely speaking, you know, there's a flow of energy this way that depends on T left to the D plus 1. There's a flow of energy the other side coming the other way. Yes, it gets scrambled in the middle, but it gets scrambled as much for the left guys as the right guys. I don't know, maybe it does factorize into T left to the D plus 1 minus T right to the D plus 1. But the hard thing is going to be to convince yourself that it is the correct answer for the physical problem. In the worst case scenario, you discover that there is a family of black hole solutions that have the steady state heat flows in the boundary, okay? On the other hand, if it can be derived by Lorentz transformation arguments, well, okay, you just do Lorentz transformation arguments. But in this case, at least in the 1 plus 1D case, it seems to hint that at least for these large NCFTs, that steady state is the unique solution, okay, at least for pure gravity. So there is some sense in which these problems can go forward. And in addition, I should say that, you know, obviously, one question is the average heat flow. Imagine we managed to sort that out. There is a question about the fluctuations, which in general involves computing all of the multi-point functions. So again, you might hope there's some simplifications on the ADS-CFT side that enable you to kind of push forward a little bit in this direction, okay? So there's clearly quite a lot of work to do, which is what I said, it's quite at an early stage. But on the other hand, I'm quite compelled by the fact that the CFT results agree with the numerics. There is a way to tease this out. And I think the nice thing about ADS-CFT is that it doesn't really care about dimensionality, but you do have to get the right solutions, right? Yeah. Yeah. Yeah, so this is, so if I go back, I mean, this was somehow the kind of matching problem that's a little bit difficult if I do it in that geometry, right? So in that case, yes, there's probably a difficulty in how you match it. However, there's various ways to view this. The first is that really, this is just acting as an initial condition for your Einstein equations. It isn't supposed to be a solution of the homogeneous Einstein equations for the whole system. So you will start it off in this particular configuration that might not be very natural from the perspective of equilibrium black hole physics, but then it will time evolve and should time evolve. And the question is, how does it time evolve? The other way of thinking about this is that one thing I didn't mention, but it was kind of implicit in what I said, but not very explicit, was the fact that if you take this formula, t left squared minus t right squared, okay, and just do the linearization, right, so just, well, even just write it like this, okay, then this is basically your average temperature. So what it says is that even in this non-equilibrium result for the heat flow, the coefficient is essentially the same coefficient you get in linear response, okay? so the actual coefficient. If it's true, this conjecture, right, which it might not be, right? There's more degrees of freedom that you could write down. But if it was true, I could similarly linearize it, and the coefficient would have to match linear response, okay? In which case, there might be better ways of getting at the quantity rather than doing this quench setup, i.e. just put a small gradient and check the heat flow. So you're not quite getting at the same non-equilibrium physics, but there's at least a few steps we can make to try and push things forward, okay? Yeah. Exactly. Exactly. So that's what I was suggesting in the second one, where you've got the left-hand side somehow at T left and the right-hand side at T right, kind of like putting some boundary conditions on your holographic setup to make a driven steady state. And my gut feeling is that one's probably much easier than that, because that involves some local quenching, as you say, stitching together these black hole solutions. But on the other hand, somehow, if the moral uptake you get from that solution is that the left-hand side acts like a heat bath and the right-hand side acts like a heat bath, then as you say, if you had a driven steady state setup, which would be probably more natural in a condensed matter context, you ought to be able to again get at the same coefficients, okay?
So this driven steady state is really, as you know, the standard case. And
Yeah.
it's also one of the most difficult for numerics, for example, because if you do numerics on a finite system, it's very difficult to process steady state solutions.
Yeah, very good. So I didn't mention that. So Joel Moore, in his 1D simulations with Karash, they're using infinite dimensional DMRG. Their two systems are actually infinite size, okay? So it's what's called IDMRG. And they're extracting these results. I actually tried to get this going myself, actually. Basically, the same day Benjamin's paper came out, I just happened to be reading it. And I tried to chase this, but just nowhere near as quick as Joel, because they've got a lot of experience in running these DMRG codes in non-equilibrium settings, okay? And so you see very clearly that, you know, there's a time scale for which, so this isn't actually stated in their paper, but it must be true. If you look at these sites, right, so if you look at site 0 and you look at site 2 reaches the steady state after site 0. So this probably corresponds to kind of light cone propagation through this system for how this steady state develops as you go through this system, okay? But nonetheless, in these numerical codes now, they do have the ability to see these steady states, okay? But even in these kind of state-of-the-art simulations, it's very difficult in some cases to rule out whether you see a steady state or if it's decaying on some much longer time scale.
That's why it would be very welcome, I would say, if you could get a true steady state solution via ADS.
No, absolutely. So I think both in equilibrium and out of equilibrium, one of the most pressing things that ADS-CFT could do is benchmark numerical simulations for strongly correlated systems. So I think one place is entanglement entropy, for example, in higher D. So the entanglement entropy has been very useful for benchmarking DMRG results. So here, as Jan is saying, I mean, actually in non-equilibrium context, you've got even fewer results. So having any analytical results at your disposal is very useful. So it provides an entry point for looking at the case where you connect two CFTs together, but then you can deform away from the critical point and see how things evolve. So I just fully agree. I mean, I think this way of kind of taking ADS-CFT into the numerical community could actually be very useful.
Okay, so before thanking Joe, we meet again at 10 past 11, I would say. So half an hour break. And let's thank Joe for a set of really beautiful lectures.